second goal on this day of section 4.4 is to deal with this thing that we're going to call the second fundamental theorem of calculus. And it says we're supposed to use it to find the derivative of a definite integral. So I'm going to jump to this next page. On this next page, we have a problem here, and I think this is a problem that we can figure out, and we could probably do it. It looks like we're supposed to take the derivative of this definite integral, but this definite integral, interestingly enough, has an upper bound that's a little goofy. That upper bound is an x, and we're supposed to be integrating with respect to t. So let's see if we can piece this together. Let's see if we can do this. So if I wanted to carry out this integral, let's see. So if I did my antiderivative of t squared would be 1/3 t cubed. Antiderivative of 3t would be 3/2 t squared. And I'm supposed to evaluate that thing going from 2 to x. So if I did that, let's see. So if I did that, I would have 1/3 x cubed plus 3/2 x squared minus 1/3 times 2 cubed, which would be 8/3, plus 3/2 times 2 squared, 3/2 times 4, would be, I think, a 6. And now we could go through and we could simplify and see what we got going here. So if we, actually, before I go any further, I forgot something. We're supposed to be taking the derivative with respect to x of all of this. So if I took this thing and I said I want to find the derivative with respect to x of that whole thing, well, wait a minute. So if we go and we take the derivative, what's the derivative of 1/3 x cubed? Derivative of 1/3 x cubed would be x squared. Derivative of 3/2 x squared would be 3x. And the derivative of either of these constants would be 0. So after all is said and done, this derivative with respect to x would end up looking an awful lot like that original function. Well, it's kind of interesting. I wonder if we just chased our tail, or what happened. Now, this doesn't do anything for us to help us understand what happens with this second fundamental theorem of calculus. And I'm going to explain it right here in just a second. But here's some information. Let's come down and let's look at this problem number 3, because problem number 3 is the reason we need this. Because this time, look what we've got. If we tried to do the exact same thing, well, I'm just going to tell you right now, that is not an integral that you know how to do. So no matter what you try to do to evaluate this definite integral, you're out of luck, because you don't know. You don't have. And in fact, by the time we're done with this class, this Calculus AB class this year, we are still not going to know how to do that integral without some sort of outside influence. So here's what happens with second fundamental theorem of calculus. The purpose of this is to take problems like number 2 and number 3 and make them a little bit easier to deal with. Now, there's some rules that go along with this. First off, you've got to be taking a derivative. Okay, some rules. You've got to be taking a derivative of a definite integral and that definite integral has to have a lower bound that's constant and the upper bound has to be a function of x. Has to be a function of x. If that's the case, if you meet all 3 of these, or all 4 of these crazy rules, like we do right here, and if you look at what we're doing, we're supposed to take the derivative with respect to x of this definite integral, and I'm going to tell you that this u is a function of x, and this a is constant. If that's the case, this is what you do. You take your upper bound, you plug in your upper bound. So this thing looks like this. If I want this solution, if I want the derivative of this definite integral without actually carrying both pieces out, I can do it in one shot. All I have to do is take my f of x. I'm going to do f of my upper bound u and multiply that by the derivative of u with respect to x. If I do that, this second fundamental theorem of calculus will give us the derivative in one shot without needing to do anything else. Show you what I mean. We already did this problem up here on the top. Problem we did up here on the top. We had this crazy function. The lower bound is constant. Lower bound is 2. If I said I wanted to do this one by the second fundamental theorem of calculus, this is what it looks like. We're supposed to do d over dx of this integral from 2 to x of the quantity t squared plus 3t dt. If I do that, I've got my lower bound that's constant. I've got my upper bound that's a function of x. I'm going to take this x, and everywhere I see a variable, I'm going to replace t with that x, with that function of x. So I'm going to have x being squared plus 3x, and I'm going to multiply that by the derivative of x, which is 1. If I do that, what I have in one step matches specifically with what I did when I took the 2 steps up there on the top. So I'm using problem number 2 to illustrate the difference, and the difference in how much work it is and how much more efficient it is to use the second fundamental theorem of calculus. I have to use it on problem number 3. I don't have a choice. Because this is an integral, we don't know how to do. So if this is the case, I'm going to take this x cubed. I'm going to go to my original function, which is the square root of something cubed plus something. And everywhere I see that something, I'm going to put in x cubed. And I'm going to multiply this thing by the derivative of x cubed, which is 3x squared. By the time I'm done simplifying this and cleaning it all up, 3x squared times the square root of x to the 9th plus x cubed. One shot, second fundamental theorem of calculus. Now it's got some crazy rules to it, but it's going to be a really nice little shortcut when you have an integral like that one that I have underlined in green right there that we really don't know how to do. So second fundamental theorem of calculus.